Okay, my dear friends, now paper October-November 2024, paper 4 variant 2, and we are starting with the physics of waves right now. A student plays violin near the doorway to a large room. Figure 6.1 is showing a young teacher standing where he can hear the sound but cannot see the student. See, teacher is standing here, student is inside the room. He can't see the student but he can hear the sound of the violin. So state the wave effect that allows the young teacher to hear sounds from the violin at the position he is standing in figure 6.1. So this is because of the spreading of the sound waves. And the spreading of the sound waves through the gap or spreading of the sound waves from the edge of an obstacle. So here through the gap we can think. So we can say right now here spreading of the waves is known as the process of diffraction. Diffraction. Calculate the frequency of the sound with a wavelength of 0.75 meters. The speed of sound in the air is given. Wavelength is given and speed is given, and this is a simple question that V is equal to F times lambda. So it means F will be equal to V over lambda. It means F is equal to 340 over 0.75. Yes, Mariam, 450 hertz. So you said 450 hertz. Okay, 450 hertz is the answer. Next is, this is a very good question. A violin produces sound in a frequency range 200 hertz to 3800 hertz, and this range of frequency is hearable, is audible to human being, because average human here can hear from 20 hertz sounds of frequency from 20 hertz to 20,000 hertz. So this 200 is within the range, 3800 is also within the audible frequency range of human hearing. The width of the open doorway is still 0.75 meters. It is not changed. Explain why the young teacher hears the frequency calculated in A2 clearly. This frequency he can hear clearly, but finds a frequency of 3500 much harder to hear. It means less diffraction. And why less diffraction? Now see, what is the condition for diffraction to take place? If you remember, with the topic of diffraction, I have shared with you lambda should be equal to d, mean the wavelength of the sound produced. If this is equal to size of the gap, if lambda is equal to d, there will be maximum diffraction and you will be hearing the sound well. But if wavelength is smaller and size of the gap is bigger, it means diffraction will be less, and it will be sound waves will be diffracting very less from the doorways, or from this one end of the one door is open, so less diffraction will be there through this gap, and he will be feeling difficulty to hear the sound. Basically this is the concept behind this. Yes, Emma, frequency is high, so wavelength is low. That's what we have to write. First of all, I will write this condition in words. When size of gap is equal to wavelength of incident wave, large diffraction is there. Large diffraction is produced. Now what is happening? Now I will be writing for the second point that for 3500 Hertz the wavelength is very small. Lambda wavelength is very small than d, size of the gap. So less diffraction. Okay, my dear friends, because speed is same. So for constant speed, wavelength is inversely proportional to frequency. So when the frequency will be increased, wavelength will be decreased and it will be smaller than the size of the gap. So less diffraction will be there and the teacher cannot hear the student well. Now, a plane mirror is placed at point X so that the teacher can see the student. On figure 6.1, draw a light ray from the violin to point X and from point X to the teacher. Draw and label the mirror also. So first of all, let me draw the line from the violin to the point X. From violin to point X. Let it be like this. So this will be basically the incident ray. No, Maria, this is not the concept. You are taking it the wrong way. Actually, my dear friend, when the size of the gap is almost equal to the size of the wavelength of the incident wave, right now here the size of the doorways or the gap of the doorways, it is equal to the wavelength produced by the sound. So diffraction is maximum and the teacher is hearing, and up to 450 Hertz frequency he can hear it very good. But when the frequency becomes above 3000, so frequency is increased, it means wavelength is decreased. So smaller wavelength and gap size is same. So gap size is bigger than the wavelength now because wavelength has been decreased when the frequency is increased for the same speed. So that's why diffraction has been decreased. So the teacher is feeling difficulty to hear the same sound of the violin at high frequency. So the key concept is this: if there is a minor difference, workable. Big difference, no. And also what I am saying, see, V is equal to F lambda. So sound, speed of sound by this violin, it is constant because it is in air. So this implies that frequency is inversely proportional to wavelength when the speed is what? Speed is same. Speed is what? Speed is same. So when frequency basically is increased in this case, so wavelength is decreased. So wavelength of the incident wave, it gets smaller than the size of the gap. For maximum diffraction, they should be equal. So it becomes smaller. So less diffraction is there, and that's why the teacher is feeling difficulty to hear the sound. Okay, so this is the first part. Now I need to draw a ray almost the same size as the, okay, first of all, better, I think there is also, they are saying draw and label the mirror, then draw an arrow to the ray showing the teacher sees the student. Okay, use a ruler to and a sharp pencil for this drawing. Okay, so it's better if I'm using some other color than red, because red will not, this one will not be visible, black one. So okay, now from first of all, from violin to point X, there should be a straight line or the path of the sound waves. So this is the incident one. Then the teacher hears it. That is incident. This is reflected, and there should be a mirror somewhere here, so I can draw the mirror and I can make it this way. So this is the plane mirror, this one is incident ray, and this one is reflected ray. So check if there is anything left to be labeled. Nothing, it's okay. Then my dear friends, this question of electricity we are not going to do, but the next question is, a fisherman uses high frequency sound waves to locate the fish in the sea. Figure 8.1 shows the small waves emitted from the boat. Then they go, state the name of the sound wave which have frequency greater than 20 kilohertz. Greater than 20 kilohertz. Yes, Mariam, good. They are ultrasounds. Waves with frequency less than 20 hertz, they are infrasounds. This is ultrasounds. Now, high frequency sound wave travels from boat through the seabed. The speed of the sound through water is this. The seabed is 22 meters below the boat. Calculate the time taken for the boat to receive the reflected wave from the seabed after the sound is emitted. So I think we should do, because there is reflection of sound, so V is equal to 2 times D over T. So making T as the subject of equation, it will become 2D over V, and then T is equal to 2 times 22 meters over speed, which is 1500 meters per second. Please, let's see it. It is 44 divided by 1500. Answer comes to be 0.029. 0.029. So I can write here 0.029, but don't forget to write seconds. Okay, my dear friends, why did I do like this? 2 times distance over time. The reason is because this is the reflection of sound. We want the time taken by the sound wave from the point of moment of emission till it goes down, hit the seabed, and then reflects back and reaches the ship again. So going and coming back, so the distance will be 2 times the distance given. Okay. Then next is see, figure 8.2 shows a fish below the boat. So describe and explain how the reflected sound wave received by the boat from the fish differs from the reflected sound wave received from the seabed. This is simply common sense. You can write here, my dear students, wave received will be weaker, will be with smaller amplitude. The reason fish is smaller, or only a small part of wave is reflected from the fish, and most of the sound wave goes to the seabed. So we will say the reflected wave. How the received wave received reflected wave. So we can say reflected wave is, we can say smaller, or better to say weaker, is weaker because fish is small and most of the incident wave or emitter wave and most the sound wave goes to the seabed. Sound wave goes to the seabed. So like this, my dear friends, you can write the answer for this. This is bit out of the way about again this part, but anyhow, no problem. You can see it and you can consider it well. If there is any question, you can ask me, please. Okay, my dear friends, stay blessed.